Hello and welcome to our discussion on Chapter 6, Input Space Partitioning. We begin by discussing what a domain is. A domain is all the possible values that can be inputted into whatever software you're using. These can be any sort of variables, any sort of objects, things like that. But that's how we define the input domain. In order to test these things, they are sort of the sum of the blocks. Blocks are just different areas of testing based on different classes and based on different partitions. None of these blocks can overlap, meaning no two tests should do the exact same thing. And in order to cover the entire domain, you must have blocks that test every single possible input feasible. Here, here partitions are defined as just groups of blocks. Um, it's a way to organize the domains and all of their test results within them. So we partition them based typically on a specific characteristic. If you were testing, we use the triangle example they use in the textbook. If you were trying to test a class or a function that required 3 integer inputs, well, you would have one section of blocks that is just testing different integers that you're putting in. You know, you're putting in 111, you're putting in 333, you're putting in 000. You might want to test then later in a different partition other values, such as inputting null, inputting letters, inputting numbers with decimals and fractions and things like that. These would all be put into separate partitions based on those sort of characteristics. It is still important that when you're making your partitions that you're again not making the same block. You're not making the same test to test the same thing in the same way. And this is where we get into input domain modeling. Input domain modeling is sort of making a map of what to test and how to test and what our partitions are. Um, for short, I'll call them IDMs for the input domain modeling, but they just represent, the domain as a whole, the whole area that can be tested, all of the feasible tests that you could possibly run. And this is where you get into the actual engineering of the tests, which is creating the partitions. How do you want to break up these tests? What sort of sections should they be in that they're readable and testable and not a big ugly conglomerate of random tests with seemingly no coercion. As before, each partition is just a set of blocks, and each block is a set of test values. You would not necessarily be saying, oh, well, a test value is the file sorted. You would have is the file sorted true is a block, and is the file sorted false as a separate block. And all of these blocks combined would be what makes up a partition. We see that there are two main types of input domain modeling, the interface-based and the functionality-based. The interface-based considers how to partition things based on more visible parameters, more tangible inputs. So, when you're writing your tests, you're writing them based on what you see in front of you. If you're using a website and it has text box to enter things in, that's a specific testable thing based on the interface. If it wants you to put in a date, it can test it based on the date. It's all based on, more visual and how the interface actually works, hence the name. For functionality-based test modeling and domain modeling, this is more of a technical approach. It requires certain domain knowledge. It requires prior knowledge to how the software is supposed to work within a system, and it is supposed to model its expected behavior. This has certain advantages as you can begin to write your test cases based on what it is supposed to do in its definition, in its user story, rather than how the interface handles once the interface is in your hand. This can be quite often more difficult because engineers and testers who are designing these models must have a more in-depth knowledge and more in-depth relationship of the systems that they're interacting with.
Now, when we think about designing characteristics of the testing functions, there are two major approaches that can be used in it. The first is the interface-based approach, and the second one is the functionality-based approach. Both of them have the different ways of being applied to a particular test function. Interface-based function is a pretty simple and straightforward approach in which only the syntax of the function is taken into place and different possible options can be calculated through it. Whereas the functionality-based approach is such a way that it is preferable for the test engineers to use different specification, different modules of how and what the characteristics can be, as we can say that it is more inclined towards the semantic, the functioning and the working of the function. In the functionality-based approach to design a characteristic, preconditions and postconditions are important. Let's say for an example, if we are traversing a list to find the maximum element in it. So one of the characteristic can be that whether the list is present or not, whether the list is null or not, or whether there is greater than one element present in the list or not. If it is not, then one element that is present would automatically be the maximum element. And in the post conditions, we can put it in such a way that if the second part of the question is that the element which we have found, is it a floating number or it is an integer number? So for that, different type of characteristics can be made. In the now, when we think about designing a characteristics, We usually divide the inputs into fewer blocks and try to include a maximum number of properties in them to complete the disjointness and the completeness between them. Disjointment basically refers to that each and every value in different partitions should be different from each other, and or union of each of them should give us the entire input domain of this test. In the following example, which is taken from the textbook, we have defined the interface-based approach, where here the parameters are only a list, and whether the list is a null or a list is an empty list, or the element is null or the element is completely empty. Here the function is such a way that it accepts two parameters. It accepts a list and it accepts an object of type element of type object, and it goes to the list and gives us whether the its given element is present in the list or not. Now, the functionality-based approach is a bit complex and it has more better characteristics than the interface-based thinking. In the functionality one, we check different things and different characteristics in a particular partition. That how many times the particular element occurs in the list, and whether it occurs in the beginning, it occurs in the end, what type of element it, and we can put in more characteristics and a lesser number of block through which we can check it in a better way. After selecting all the characteristics, the testers have to partition the domain of these characteristics into a different set of values, and these sets are known as blocks. So if we have more blocks in our function, it will result into more tests, it would require a lot more resources, but it would help us find more and more faults. And if we have less number of blocks in our function, it will result into a less number of tests. It would result into less amount in consumption of the resources, but the effectiveness wouldn't be that high. For any block generation method, or how we can make blocks, or what value should be in there, there are different properties as stated below. In each and every block, either one, two, or three properties, or even more, all of them can be applied. First is valid and invalid values. So each and every block in its partition, we can say, should have all the values that should be ranging from the beginning to the end in it, whether they are the right values, they are the wrong values. By that, we could be able to get a particular invalid or valid output, and we could test it. Subpartition method. All the values which are valid should be partitioned in subpartitions, and those partitions, the subpartitions, should be in such a way that the value and the functionality of that value, that I'll explain by an example, that if in one partition there are only discrete values and in the other one there are floating values, so accordingly, depending how they act on our function, we can know that whether our function is correct or not. Boundary values. So usually what happens is that when we take a set of inputs and all of them are in a contiguous manner, that the output is like, for example, we are getting output A, B, C, D. We have to classify between A, B, C, D. And if A accepts value from 0 to 1, B accepts from 0 to 2, A accepts from 0 to 1, B accepts from 1 to 2, C from 2 to 3, and if we ever input the value 0.99 bar, so at that time if our function is not correct, then we might get an ambiguous value between A and B. So this helps in removing that type of errors. Balance is a form of adding blocks method. As we discussed, that adding blocks help us to increase the effectiveness. So the more amount of blocks we add, the more varied values we can compare with the given values, and the better our test results will be. Missing blocks. Now, missing blocks is in such a way that we shouldn't miss out any block or a partition while checking this function. We should cover each and every value that is present in our input domain, and the way we can check that we have included all the blocks is by taking the union of all the blocks or the partition we have in such a way that when we take the union and it covers the entire input domain, that means that we have taken and included all the blocks. If it doesn't, then we might be missing something. Overlapping blocks. We have to check that in each and every partition and blocks there aren't some similar values, because as this partition should be disjoint in nature, we cannot or we shouldn't include repetitive values in different sets.
Checking the input model domain model. It is very important to check the input domain model. In terms of characteristics, the test engineer should ask whether any information about how the function behaves is not incorporated in some characteristics. This is necessarily an informal process. The tester should also explicitly check each characteristics for the completeness and disjointness properties. The purpose of this check is to make sure that for each characteristic, not only do the blocks cover the complete input space, but selecting a particular block implies excluding all other blocks in that characteristics. If multiple idioms are used, completeness should be relative to the portion of the input domain that is modeled in each idiom. When the tester is satisfied with the characteristics and their blocks, it is time to choose which combinations of values to test with the identified constraints among the blocks.
Today we are going to discuss combination strategies criteria. When we start discussing about this criteria, this situation, then a question evolves that how we should consider multiple partitions at the same time. Basically, there are a total of 6 strategies, which are combination coverage, each choice coverage, pairwise coverage, T coverage, base choice coverage, and multiple base choice coverage. The most obvious choice is to choose all combinations, but however, using all our combinations will be impractical when when more than 2 or 3 partitions are defined. So here is our first strategy: all combination coverage. For all combination coverage, we must consider all combination of blocks from all the characteristics. Let us consider an example with 3 partitions with blocks A, B, 1, 2, 3, and XY. For this, we get 12 tests, which are A1X, B1X, so on up to B3Y. Number of tests is a product of number of blocks for each partition. So, for the above example, there are 12 tests, which can be mathematically defined as pi I of 1 equal to QB1. So let us think if we have 4 blocks, then we should get 64 tests. This is practically more, and there happens to be practically more testing. So it will be a economically impractical one. This is our second strategy: each choice coverage. In each choice coverage, one value from each block for each characteristic must be used at least once in each test case. Now let's consider the same example which we used for the above strategy, which is 3 partitions with blocks A, B, and 1, 2, 3, and XY. There are many ways to satisfy ECC, of which they are A1X, B2Y, and A3Y. For mathematically explaining the tests, maximum number of tests for ECC, here we consider there are Q characteristics, and each has a block B I. Then the test sets that satisfy ECC will have at least max of I equal to 1 QBI values. The weakness of ECC can be expressed as not requiring values to be combined with other values. So the problem with ECC is that it leaves a lot of flexibility to the tester in terms of how he combines the test values. So this is a weak strategy. So uh, we go to the next strategy, that is pairwise strategy, where we require only explicit combination of values. Here we come to our third strategy, pairwise coverage, which is the next version of each choice coverage. Here in pairwise coverage, a value from each block for each characteristics must be combined with the value from every block for each other characteristics. Given 3 partitions with blocks A, B, 1, 2, 3, and XY, then PC will need to test to cover a total of 16 combinations. For example, A1, A2, B1, B2, 1X, 1Y, which leads up to A1X, B1Y. A test sets that satisfy PC will have each other's value, or at least the product of max of I equal to 1 into QBI and max of I equal to 1 of QBI values. A natural extension to pairwise coverage is to require groups of T values instead of pairs. So our next strategy is T-wise coverage. In T-wise coverage, a value from each block for each group of T characteristics must be combined. If we assume that all blocks are of same size, a test set that satisfies T-wise coverage will have at least max of I of QBT values. But T-wise coverage is expensive. Is the test case going above 2? That won't be helpful. Both pairwise coverage and T-wise coverage combines blindly without knowing which values are combined. strategy. Base choice coverage. Base choice coverage strengthens each choice coverage in a different way by bringing in a small but crucial pieces of domain knowledge of the program. A base choice block is chosen for each characteristics and a base test is performed by using the same base choice for each characteristics. Subsequent tests are chosen by holding all but one base choice constant and using each non-base choice in each other's characteristics. For example, if the blocks are A1 X are the base choice, X is the base choice, X the base choice is A1X. Non-base tests can be B1X and A2X. Now here comes to the number of tests. A total of one base case and summation of I equal to 1 Q of Bi minus 1 non-basis cases are required to satisfy BCC. Combining more than one invalid value is usually not useful here. If the base choice contains valid inputs and non-base choice are invalid, then BCC is an easy way to achieve stress testing. Multiple base choice coverage. This is an extension to base choice coverage. In sometimes the testers may have trouble choosing a single base choice and may decide that multiple base choices are needed. So then we use multiple base choice coverage. At least one and possibly more or base choice blocks are chosen for each strategy, and base tests are performed by using each base choice for each characteristic at least once. Subsequent tests are chosen by holding all but one base choice constant for each base test and using each non-base choice in each other's characteristics. Multiple base choice requires m plus 2 sigma of I equal to 1 q of m into b of I minus mi tests, where mi is the number of base choice, m is the total number of base tests. So finally, this is subsumption relation among the input space partition criteria. This is all the strategies that we discuss in the above slides.
In this, we will work on example of constructing an IDM and designing tests for widely used Java library interface. For this, tester should have enough knowledge on product in order to create test cases, as we need input parameters for testing and analyze the output to the expected output. JUnit tests can be made from Javadoc APIs in three main tasks. Task 1: determine characteristics. Task 2: define test requirements. And the final task is to refine test requirements into automated tests.
Tasks in designing IDM based tests. The first task is to determine the characteristics, that is to identify the following and document them in table A: functional units, and the second one is parameters, and third one is return types and possible return values, and the final is the exceptional behavior. And task 2, define test requirements. First, we need to choose a coverage criteria and then choose base cases if using BCC or MBCC and document this in table B. Design complete test requirements. This is documented in table C. Identify any infeasible test requirements and document those in table C. If using BCC or MBCC, revise any infeasible test to create feasible tests and document them in table C. And then we have the task 3, in which we refine test requirements into automated tests. Using the final test requirements, write a JUnit test for each infeasible test requirement. Each test requirement must map to one test. Although it would be impossible to satisfy several test requirements with one test, we choose not to do that in this example to keep the tests and mappings simple to follow.
As mentioned in the earlier slides, IDM designing involves three tasks. In this example, the first task is to determine the characteristics of iterator. The iterator interface has three methods. The first method is hasNext. It returns true if the iterator has more elements to iterate. The second method is next. Returns the next element in the iteration. We can get one possible exception in this method, that is no such element exception. The third method is remove. Removes the most recent element returned by the iterator. This method can throw two exceptions. One is unsupported operation exception and illegal state exception. This is the table representation of the methods mentioned in the previous slide. Here we can see the next method is covered by hasNext method, which means we should check hasNext method before executing next method. In this, we can see the method and their characteristics. hasNext has one characteristic, that is more values. Next has two, remove has four. We can see the base cases and partition cases. The second task is to define the test requirements for iterator. In this, we choose base choice coverage. We make the base case a happy path test where everything should work normally without exceptions. In this table, for each method, its characteristics are listed, followed by the test requirements that are needed. The only characteristic for has next method is C1. So it has only two test requirements. The first is the base case where the iterator has more values, and the second is the non-base case. Next method has two characteristics. So each test must choose a value from each of C1 and C2. Again, the first test requirement is the base case where both C1 and C2 are true, and then each is varied in turn to create three test requirements. Remove has four characteristics, so five test requirements are needed. Next thing we need to do is revise the infeasible test requirements. hasNext has none, but next has one. If C1 is false, the iterator is out of element, so iterator cannot return a not null object reference, meaning C2 cannot be true. The same problem occurs in the second test for remove. We can revise the infeasible test requirements to make them feasible by applying the fix suggested in revised TRs column. For next, we can change the test requirement from false true to false false, which means C1 and C2 both are false. And for remove, we can change false true 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 to false false true true. The last task is to refine tests into automated tests. The result at this point is two test requirements for hasNext, three test requirements for next, and five test requirements for remove. Each test need to be refined into a concrete test case, including a verification of the output. Iterator is simply an interface, and Java interface are not directly executable. Hence, to develop concrete tests, we need an implementation of iterator. In realistic testing situation, it would be obvious which implementation we were testing, namely the implementation we were developing.